So, before we get to Chris's comment about what this is going to do when we curve a wire, we're going to look at the situation when we've got two wires that are nearby each other. Since this, I guess, was our first comment about how this is important to our lives as engineers, is crosstalk between wires. So all current carrying wires are going to create a magnetic field. It's important to know how that affects nearby wires. So let's say we've got two long wires a distance r apart, carrying currents I1 and I2. In my calculations here, I1 is the bottom wire and I2 is the top wire. This picture from the book uses I and I prime, which I think is a little confusing. So I've used subscripts I1 and I2. So let's first look at the magnetic field due to the bottom wire, that's caused by the bottom wire, acting on the top wire. So our right-hand rule shows that the B field is going to curl around the bottom wire, and at the top wire, the B field is coming out of the board. So if we use our right-hand rule, the top wire's current is going to the right, the B field is coming out of the board, and as this picture shows, that means that the force due to that magnetic field is going to be down. So if you've got these currents flowing in the same direction, the force between them is actually going to be pulling them together. So let's find out the value of that force. So the force on the top wire due to the bottom wire is I2, that's the current in the top wire, the length of the wire, crossed with the magnetic field due to the bottom wire. The cross product spits out 90 degrees, so we can drop sine of 90. So we've got I2, the length of the wire, times the magnetic field due to the bottom wire. Biot-Savart law we throw in here. That's the magnetic field we just derived for a current carrying wire. Mu naught I1 over 2 pi r. And then we nicely summarize that into a single fraction. So that would be the force on the top wire due to the bottom wire. Oh, I forgot L in there. All right. Is there anything in this equation that tells you that that's the force on the top wire due to the bottom wire? Jordan shaking his head no.
Either one.
Yeah, it's got both the currents. It's got a length, but we're assuming the wires are the same length. The distance r is the distance between them. So this equation, you could rederive it for the force on the bottom wire due to the top wire, but you get the same result. So the force between the wires is equal and opposite. Both wires experience the same force, and this equation doesn't really indicate which force is which. So this can be used for both wires. And so this will just give you the magnitude of the force. In order to figure out the direction of the force, then you've got to kind of logic through it with your right-hand rules. So this used two right-hand rules. The first was looking at the bottom wire. We used our simplified right-hand rule to figure out the curl of the B field due to that bottom wire. That means it's coming out of the board for the top wire. Then we had to use our physics gang sign to figure out that if that was true, our force is pointing down. So you can kind of walk through the logic for other situations as well. But what we've learned here is that for two currents that are in the same direction, the forces are going to be pulling towards each other. And if you've got one of the currents in the opposite direction, then you'll find that the forces are repelling each other. So currents in the same direction attract, and currents in opposite directions repel. All right, so now that you have that information, see if you can figure out example 28.5 with your groups.